So today I'm going to tell you about some of my group's research in both carbon nanotube and graphene nanoribbon electronics and overcoming the material science challenges towards those goals. So since this is an awards talk, I thought I would start off by first thanking some of the mentors that really have helped me through my early career. As an undergraduate student, I conducted research first with Joe Lighting at the University of Illinois. Joe was really the one who first exposed me to that the research world even existed out there. I was just an undergraduate going through classes, and he exposed me to this fantastic world of science and engineering, and I'm very grateful to him. For my graduate studies, I spent some time with Fedor Navoris at IBM Research in the early 2000s, kind of at the very beginning of nanotube electronics. And then conducted my PhD with Professors Mark Hersam and Sam Stupp at Northwestern. I was co-advised by both of them, and finished then with a postdoc at the University of Michigan with Steve Forrest, where I learned a lot about organic electronics. So I'm very grateful to all these mentors. I'm also grateful to mentorship I've received from the Nanocarbons division at ECS. I'm on the executive committee of the Nanocarbons division, and I've been participating with them over the last 10 years substantially, and they've also given me a lot of mentorship as well. So I'd also like to acknowledge some of our collaborators for the work I'm going to tell you about, especially Professor Padma Gopalan, Changwoo Zhou, Martin Zani, Nathan Geisinger, Mark Hersam, Richard Martel, Osama Montanabir, and a number of others. And support from NSF, Department of Energy, and the Army Research Office in particular. So I thought I'd say something a little bit about Charles W. Tobias that the award is named after. So this is from the Electrochemical Society's webpage. So he's born in Hungary in 1920, and he was a professor at UC Berkeley for almost 50 years. And he really was foundational in research in electrodeposition, electrophoresis, and scale-dependent processes associated with these kinds of systems. And he served a number of roles in the ECS, including vice president in 1967 and president in 1970. And so it's really an honor to receive this award in his name. OK, so let me transition to what I want to tell you about today. So my research group is all about overcoming the material science challenges to nanocarbon materials. So we are really focused on carbon materials derived from graphene, and we're taking this in multiple different directions. So in our carbon nanotube research, our work focuses on sorting of nanotubes between metallic and semiconducting types, and by diameter and chirality and band gap, controlling length, and then controlling assembly to make high-performance field effect transistors. Okay? That's going to be the first part of my talk. We also have a significant effort in then using these same semiconducting nanotubes as the light-absorbing components of photodetectors and solar cells. I won't have time to talk about that today. In the second part of my talk, I'm going to talk about using graphene, but shaping it into nanocrystals of nanoribbons. So nanoribbons of graphene that we're able to grow from the bottom up and control their alignments to create semiconducting arrays of graphene nanostructures that are much like these carbon nanotube arrays, but composed of thin strips of nanoribbons. Okay? So this is really a synthesis and a synthesis story. Okay? We also have some work on making 2D laminates of 2D materials for chemical separations, which I also will not have time to talk about today. So really the vision of the two areas I want to tell you about are that these nanocarbon materials are really exceptional conductors of electricity. They're exceptional semiconductors. But they haven't made it into the commercial applications because of material science challenges. So to use nanotubes in electronics, you need to organize them into aligned arrays. So this is like what the ideal transistor for a carbon nanotube might look like. You have ideally aligned arrays of all semiconducting nanotubes of all the same type. And likewise, if we can make arrays of identical nanoribbons that are semiconducting, And on a wafer scale, only then could we really impact the technologies. There's really tremendous material science challenges in how do you organize and assemble and synthesize materials in these ways. So looking in particular in the challenges that carbon nanotubes face, so we have this heterogeneity problem. So this is a powder of as-grown nanotubes. In that powder, this is grown by the HIPCO method. There are some 40 different diameters and chiralities or chiral twists of nanotubes present. And the electronic properties of each one of these nanotubes is different. So you have increasing diameter means decreasing band gap. Some are metallic, some are semiconducting. Also, these tubes are all tangled together. So the question is how can you line them up into arrays? You really need them to be aligned in arrays to fully exploit their properties in transistors. And not just alignment matters. We need to control the pitch between the nanotubes as well. So for example, you don't want more than one nanotube every 5 to 10 nanometers, and you don't want less than that. So there's an optimal pitch. Too many nanotubes leads to interference effects between the nanotubes, and you can't fully modulate their conductivity. Too few nanotubes mean you don't have enough material in your transistor channel to make a good high conducting channel. So the way we overcome this heterogeneity problem in my group is to use chemistry. So the physical difference between different nanotubes is very minuscule. So here are, to scale, 5 different structures of nanotubes present in this mixture of some 40 tubes, different types of tubes. They're to scale. So the difference in diameter between these two, for example, is one is 8.25 angstroms, one is 8.29 angstroms in diameter. That's only a 4 picometer difference in diameter. Yet electronically, these two tubes are dramatically different. So this tube is metallic and this tube is semiconducting. These two tubes have the exact same diameter, 5.75 angstroms, and they have different band gaps. So physically, there's very few differences between nanotubes. But electronically, there are much larger differences. And so we use chemistry that's sensitive to the electronic properties of the tubes to sort and differentiate among all these different types of tubes. Okay? So the chemistry that we use in all the research I'm going to talk about today is to use conjugated molecules like this polyfluorine bipyridine copolymer, PFO-BPY. So these polymers were first investigated by Jeff Blackburn at NREL. And it's possible to take a powder of these heterogeneous nanotubes, mix it with this polymer, and this polymer will selectively stick to semiconducting nanotubes. There's a very strong affinity over metallic nanotubes. And from this black powder, you could extract, for example, here, this pink solution. The color, this pinkness, is not coming from the polymer, it's coming from the semiconducting nanotubes, which selectively absorb in the non-pink color range. Okay? So you could take an optical absorption spectrum of this solution, and you see where the semiconducting nanotubes absorb here and here, and the metallic nanotubes, if they were present, would be absorbing here. And we know from this absorbance spectrum that we've reduced the metallic nanotubes to less than 1 part per 100. And what we've done in my group is to use transistors where we've measured nanotube by nanotube very laboriously. And we've measured over 20,000 nanotubes and have yet to find a metallic nanotube. So that means that there are over 99.99% semiconducting nanotubes in these solutions. So we were able to overcome the heterogeneity problem by using this chemistry, and we were able to create these very high purity semiconducting nanotube inks. We've also spent a lot of time studying not just how pure the nanotube solutions are, but how these polymers interact with the carbon nanotubes. So here we've used polarized fluorescence spectroscopy, where we excite the backbone of the polymer at one particular polarization, and then look at fluorescence from the nanotube at a different polarization. And we're able to extract that the polymer adopts a 12-degree wrapping angle around the tubes. And we're also able to gauge how much polymer sticks to the tubes. And the coverage of the polymer on the nanotube on this y-axis as a function of how much polymer you have in the solution. This is excess polymer in your solution. Follows what's called Langmuir absorption isotherm behavior, where the coverage increases with free polymer in solution according to this equation. There's cooperativity, and you see that there's a saturated coverage at around 3 grams of polymer per nanotube on the surface of the tube. So you could do this for both metallic and semiconducting nanotubes, and what you see is that the binding affinity, which you could extract from around the half coverage point, is much stronger to semiconducting nanotubes than metallic nanotubes. So this explains, in some part at least, the differential selectivity of these polymers for semiconducting over metallic nanotubes. All right, so the other challenge then is how do you align nanotubes? You have the solution of very high purity semiconducting tubes. How can you align them on substrates? So we've, in my group, in collaboration with others at the University of Wisconsin, including Professor Padma Gopalan, have investigated a number of different solution-based processes for depositing aligned arrays of nanotubes. And we kind of stumbled upon a new approach for organizing nanostructures that uses fluid-fluid interfaces in combination with flow to induce alignment. And we've named this process floating evaporative self-assembly, or FESA. And in FESA, we take our nanotubes, which are an organic solvent that's immiscible with water, specifically chloroform. We drop this chloroform onto an aqueous subphase, a water trough, a beaker full of water. And when the chloroform spreads, it spreads very rapidly into an ultra-thin layer that's about 100 microns thick. It spreads over an area of a couple centimeters. This is a microliter droplet that spreads over a couple centimeters squared area in a 30th of a second. So this frame rate of our camera. It spreads very quickly. And practically what you see is that when this droplet spreads, it comes in contact with a substrate that we're pulling out, and an aligned array of nanotubes is deposited onto the substrate. And in the first iteration of this, what we did was we just kept iteratively dropping microliter by microliter onto this aqueous subphase, resulting in stripe after stripe of aligned nanotubes. Okay. So this is what the arrays look like. You can make it out somewhat in this on the projector. You see around 40 tubes per micron in this case. The concentration of tubes is dictated by the concentration of tubes in the solvents and in the spreading rate and other factors. AFM shows that the tubes are mostly individualized and they're aligned within a 14-degree window. Okay. So we were able to scale this to about a 25 by 25 millimeter area of it. So we deposited these on a silicon wafer. Each one of these droplets of ink produces a stripe of aligned nanotubes. So here they're aligned nanotubes, and in between the stripes you get these random nanotubes. And I'll tell you why that is in a second. So these aligned nanotubes are perfect for field effect transistors. So one of the goals in the carbon nanotube electronics field has been to make transistors and circuits better than silicon circuits. But that's actually been very, very difficult because of metallic tubes, because of difficulty aligning tubes, because of difficulty controlling your packing density. So all transistors made from nanotubes have actually been worse than silicon up till a couple years ago. So these aligned arrays of nanotubes are all semiconducting. They're individualized. That means when you deposit source and drain contact materials like palladium on top of the tubes, the palladium will blanket each tube. So this is a cross-sectional TEM where you see the individual cross-section of the nanotube here. So each tube is being blanketed, which means you can make very good electrical contact to each tube. They're semiconducting and they're aligned. So we're able to make field effect transistors from these that are very high performing. Okay? So here are the typical transfer and output curves. I'll just say quickly that high on-state conductance is realized, saturation is achieved, and we're able to achieve high on-off ratio. So if you compare this to the state of the art in the field, what you'll see is that this is two metrics extracted from those current voltage curves. This is the on-off ratio of the transistor versus how conductive it is when it's turned on. You want silicon is somewhere up here. So you can see that state-of-the-art of field, it's been very difficult to come anywhere near silicon, and there's always been a trade-off between having high on-off ratio and high on-conductance. But what we're able to do with these aligned arrays is to be able to push this data up to the upper right, and we're able to make arrays with performance on par with that of silicon. If you analyze the conductivity of our arrays on the per tube limit, you see that we're able to achieve conductivity on the order of 1 quantum conductance unit. So that means we're achieving near ballistic transport through each nanotube in our arrays in parallel. This is about as good as you could possibly do per nanotube. So we've translated the exceptional properties of nanotubes that have been known on the individual scale. So for 20 years or so, people have been making fantastic transistors from one nanotube, but we've been able to translate that to parallel arrays of nanotubes, which is what you need for technology. So benchmarking this against silicon, so this is the gate voltage normalized by the oxide thickness. This is the on-state current. So when normalized so that so an apple-to-apples comparison in the off current is the same, we're able to achieve 1.9 times higher drive currents than silicon for a slightly longer channel length. Okay? So this is a really cool result in which we've been finally able to achieve a transistor that outperforms silicon using aligned arrays of semiconducting carbon nanotubes. Now these transistors can be used to compete with other technologies like 3.5 materials and RF amplifiers. So this is work with Chongwu Zhou at the University of Southern California, where we've given them our aligned arrays of tubes, and they've integrated them into RF devices and able to increase the Fmax and Ft to over 70 gigahertz at the same time. And another application for these aligned arrays is in thin film transistors for flexible electronics or plastic electronics. We're able to achieve charge transport mobilities of over 200 centimeters squared per volt second, which is really excellent for a thin film semiconductor. It really blows away current thin film semiconductors like amorphous silicon or IGZO. So it's a fantastic material for many applications. So I'll just quickly say something about the mechanism. What's causing the nanotube alignment during this floating evaporative self-assembly? So we worked with a colleague in mechanical engineering, Argentile Berson, who was able to set up a camera, and we used a transparent substrate instead of a silicon substrate. We were able to look through the substrate at the fluids. So what you see here is water, the chloroform as it's spreading in the air. We're able to look at this in real time using a high-speed camera now at around 10,000 frames per second. And we're able to track the positions of these interfaces as we're adding these doses of ink. So this is time. We're adding doses of ink here, here, and here. And you can see that these interfaces are moving up and down. And we're able to then correlate that with where the nanotubes are depositing in these aligned stripes. And what we learned from these studies, it's kind of hard to interpret these data on the fly, but what we learned is this, that when we put the nanotube ink on top of the water, the contact line where the water meets the air suddenly drops by about 100 micrometers. The nanotubes accumulate at the interface between the organic solvent and the water, much like soap would go to a water-organic interface. The nanotubes accumulate there, and they go from randomly aligned in 3D to they're just aligned and randomly aligned in 2D, and then they stick to the substrate in these aligned stripes. Okay? And then when the stripe moves up, it pins the contact line, pulls everything up, which you see kind of here, and then the process happens again when you release a new droplet. By studying this interface, we think we know how to then create a continuous version of this floating evaporative self-assembly where we achieve substrate complete coverage of aligned nanotubes of the substrate, but I can't tell you about that today. Another big issue is how do you remove this polymer wrapper once it's on the nanotube? Here we've collaborated again with Padma Gopalan's lab, and she's developed two things. She's developed a degradable polymer. She has a degradable imine group in the backbone of the polymer that degrades with mild acid treatment. We've also shown that this PFO BPY can be just stripped right off the nanotube surface by complexing the bipyridine with rhenium salts. The rhenium salt coordinates with the bipyridine, changes the stiffness of the polymer. It can no longer wrap the tube. It will just come right off either in solution or in arrays. This is important if you want to, say, make a biosensor from carbon nanotubes, where you want the surface of the nanotubes to be clean after you've deposited them. OK, so I'm just going to check the time here and transition now on to the second part of my presentation, which is where we're trying to do the similar thing, make arrays of semiconducting carbon, but this time by growing nanostructures of graphene or nanoribbons of graphene instead of nanotubes. OK, so why nanoribbons? So they have many of the same promising charge transport properties as nanotubes. Tunable band gap that varies with width, high current carrying capacity, high carrier mobility, high thermal conductivity, and some orientations of nanoribbons can have magnetic and spin polarized edge states. So new phenomena are also possible. They're not possible in nanotubes without edges. So, but the major challenge here is in synthesis. So bottom-up synthesis is needed. Originally, it was envisioned that you could grow large area sheets of graphene and then use lithography to pattern it into nanoribbons. But this doesn't work very well because, first of all, the width of these ribbons in order to have semiconducting nanoribbon needs to be less than 10 nanometers. And that's pretty difficult to achieve with any conventional lithography. And then secondly, you need smooth edges. And when you use lithography to create a graphene nanoribbon, you typically get rough edges with disorder. So you need smooth edges, really narrow widths, and the band gap varies with crystallographic orientation. So the largest band gaps occur for armchair directions, so you ideally want armchair nanoribbons. So you need a bottom-up synthesis instead of a top-down lithographic approach. There are a number of bottom-up synthetic approaches that are being developed out there right now, including polymerization on surfaces, unzipping of nanotubes, lateral heteroapitaxy. Won't say too much about these, but they all face challenges. Okay? So we are investigating a different approach, which is to directly grow nanoribbons by hydrocarbon, for example, methane, chemical vapor deposition, where instead of growing a hexagon crystal of graphene, which you might get on most surfaces, we're exploiting substrate graphene interactions, so the interactions of a graphene crystal with the substrate, to control the kinetics of the crystal growth so that the crystals grow very quickly in one direction but very slow in another direction. So anisotropic growth kinetics. So during graphene CVD, a number of complex processes happen. So your hydrocarbons deposit, they'll decompose into CXHY species, a variety of which will exist. These will diffuse around on the substrate. They'll eventually nucleate a crystal of graphene. This crystal will grow. You'll get nucleation in multiple points. You'll get some sort of polycrystalline continuous layer of graphene in the end. Okay, so what we're most interested in this project is this initial stage. When the crystals start to evolve, what shape do they evolve in, and how can we control that? So we've studied this a lot on copper. We have several papers studying this crystal evolution on copper. And what we learned is that the shape evolution is dictated by a number of factors, including the symmetry and facet of the surface, nucleation density, the edge termination, and the catalytic breakdown pathway of your hydrogen precursor. Here are different crystal shapes we've observed on copper by varying these factors. So you can see that you could tune the crystal shape pretty dramatically, reading dendrites, flowers, hexagons, rectangle-like things, circles, squares. Many, many different shapes are possible. So we then started studying similar phenomena on other surfaces. And in particular, we started looking at germanium single crystals as a catalyst and a substrate for graphene synthesis. And what we observed is on germanium 001 surfaces, these are crystals of graphene in dark, and the light is the germanium. This is methane, CVD at 910 C, and argon and hydrogen environment at atmospheric pressure. What we see is that as we cut the amount of methane and slow the growth rate down, that the crystals of graphene that nucleate are growing highly anisotropically. They're growing very quickly in one direction, for example, 200 nanometers per hour in this direction, but very slowly in the orthogonal direction, like 5 nanometers per hour. So this is an aspect ratio of around 40. So the crystals are, in fact, actually growing directly into the shape of nanoribbons. Okay. So the width of these ribbons slowly increases with time. We can simply tune the width by controlling either growth time or growth rate. So here's an example of an STM image taken by Nathan Geisinger at Argonne National Lab of a 10 nanometer wide ribbon that's several hundred nanometers long. We grew this in Wisconsin. We transferred it through air, through the mail to argon, and then it was baked out. What you see here are germanium oxide features surrounding the ribbon. Underneath the ribbon, you see steps in the underlying germanium. I'll talk more about that later. Okay? We've made ribbons as narrow as 1.7 nanometers with this approach. and really huge aspect ratios possible. So here's a single ribbon that's 6 nanometers wide, that's 1,300 nanometers long. So what's really pretty interesting is that these ribbons are self-orienting on the germanium 001 surface. They seem to be, just looking at these SEM and AFM images, oriented either along the 110 or the 1 bar 10 directions of the germanium surface. Okay? You see also these facets, these steps in kind of structuring, nanostructuring the germanium that occurs underneath the nanoribbon. I'll talk more about that later. You see that the ends are at 60 degrees from the edges, so that means all the short ends and the long ends, edges all have the same crystallographic termination. And you see about 45% of the crystals of graphene and nucleates are oriented horizontally, 45% vertically, but about 10% of the time you get these low aspect ratio crystals. And we now know why this is. So we collaborated with Osama Motanabir and Richard Mattel and Patrick Desargin in Montreal and Polytechnique Montreal to analyze the crystallographic orientation of these ribbons via low-energy electron diffraction and microscopy. So this is the lead pattern of the germanium surface and of the graphene surface, and you could look at the relative angles between these two to determine that all of our nanoribbons are armchair ribbons. So the carbon-carbon bonds are pointed along the long axis of the nanoribbons. We also conducted dark field microscopy to confirm this, but there's a little complexity here. What you see in the graphene diffraction is a double spots here. Okay? This actually says that we have 4, not 2 orientations of nanoribbons. We have 2 orientations that are roughly vertical, 2 that are roughly horizontal, split by plus or minus 3 degrees. And we don't know why this is yet. Okay, so we have this plus or minus 3 degrees. So these are 4 orientations we see. They're all armchair ribbons. And then here's some more STM images. So we see that there's steps in the underlying germanium. The germanium adopts a 2x1 reconstruction underneath the nanoribbon. We see that the edges are armchair and that they're relatively smooth, so the width of the ribbon varies by only 1 lattice constant of graphene over length of the ribbon of 40 nanometers. It's much smoother than you could get with lithography. Here you see the graphene lattice. Here you see electron interference effects due to scattering off smooth armchair edges. So you only see this pattern for smooth armchair edges. So we've shown that these ribbons can indeed be semiconducting. We've made field effect transistors from them 1 ribbon at a time, much like our nanotube transistors with the silicon oxide backgate and palladium electrodes. This is the conductivity of the ribbon, conductance versus gate bias, a constant source drain bias. As you make the ribbon narrower from 50 to 23 to 12 nanometers, the off current goes down, showing you're opening a gap, whereas the slope here, the transconductance doesn't change, which means that as we're making the ribbons narrower, we're not introducing new scattering off the edges. And that's exactly what we wanted to see. Further evidence that we have relatively smooth edges in our ribbons. We were able to create ribbons with an on-state conductance of 5 microsiemens and an on-off ratio of 2 times 10 to the 4th at room temperature. This is really state-of-the-art for any nanoribbon that's been grown or synthesized, like, for example, in comparison with ribbons that have been polymerized. Okay? So we published this last year. So we've also learned a lot about the mechanisms that are driving this anisotropic synthesis. And we've done that by seeding the synthesis. So what you see here are little dots of graphene seeds. So we're able to grow graphene, single crystals of graphene on copper, transfer them onto germanium, and then use e-beam lithography to make little seed crystals that are down to 10 nanometers in diameter. But what's really cool about these experiments is that we could rotate the crystal of the seed with respect to the germanium. So here we're looking at the armchair direction relative to the germanium 110 direction is 2, 7, 15 degrees. We're able to rotate this and learn something pretty fundamental here. Okay? So what we see is that when this angle between armchair and germanium 110 is small, like 2 degrees, all the seeds evolve anisotropically into nanoribbons. But when this is larger, 15 degrees, all the crystals evolve as rhombi, so low aspect ratio structures. And in between, you get a mixture of ribbons and rhombus-like features. Okay, and we've studied this over hundreds of nanoribbons. We could break that down even into something more fundamental. We could study the growth rate of each edge of a crystal as a function of that edge versus the germanium 110 direction. So here's 2, 10, and 13 degrees. We've measured this for 640 crystals. And what we see is that this picture is simply that the growth rate of an edge depends on the angle between the armchair direction and germanium 110. So it's nearly zero growth rates for zero angle, which increases as you increase that angle to 45 degrees, and then it'll decrease again back to zero. Okay? So from this information here, we could predict the shape evolution of any seed as long as we know its crystallographic orientation with respect to the germanium. So seeding then allows us to make unidirectionally aligned arrays of nanoribbons. So here we've created ribbons that are all vertical, and we're able to eliminate these horizontal ribbons and these low aspect ratio crystals we see around 10% of the time. We're also able to reduce the polydispersity of the nanoribbons because without seeds, the nanoribbons nuclei start growing at different times and they have different widths. But by starting all at the same time at t equals 0, they have much more homogeneous widths and lengths. Okay? We've also learned something about the nucleation process. As you make the seed diameter smaller, the ribbons become narrower, but something else interesting happens. Okay? So when you have this germanium 110 direction and the armchair direction offset, and the seeds are large, you get these rhombi like I told you about. But that's only true when you have a large seed. What we discovered is that as you make the seeds smaller and smaller, the seeds are able to rotate. Then they rotate to the more favorable direction where the armchair direction is parallel to the germanium 110, and you get a nanoribbon. So as you reduce the seed diameter from 20 to 15 to 10, you go from rhombi to nanoribbons again. But the nanoribbons are oriented both vertical and horizontal now because they're freely rotating as they become smaller. So this means the ribbons form due to two factors. One, anisotropic kinetics that depend on this angle, and two, the nuclei, which are probably true of the spontaneously generated nuclei as well as the seeds. They're able to rotate and lock into interjectly favorable orientations, where the favorable orientations occur for armchair parallel to germanium 110. Okay? So we think that this anisotropic crystal growth is an exciting direction for synthesizing graphene nanoribbons and nanoribbons arrays. They have smooth edges, self-aligned, high aspect ratio, excellent transport properties. They're an imitable complex pattern and array formation via seeding. And what's really cool is that this is all happening on a commercially viable semiconductor wafer platform, germanium. In principle, should also be possible in germanium on silicon, and therefore should be a promising pathway to hybrid carbon silicon electronics. Okay? So I'd like to thank again my group and my collaborators and financial support, and thank you very much.